Right. So we are here for Tim Keebler's defense, like do I need it?
Yes.
And so unlike many of my other students who came from China, he's actually coming from Pennsylvania. And he had a major in meteorology, which I was very suspicious about. But then he had a internship with Mike Limon, and he was very happy with him. So also his grades happened to be like 4.0, if I remember correctly. And that convinced me to hire him, and I was not disappointed. He worked very hard on two different projects, and one of them was one of my major grant, freelance grant, which is about modeling extreme space weather events, and he will talk about his work. He really contributed a major part of that project. So you are the lucky ones because Zoom doesn't work, and we will actually hear what he has to say. And questions will be asked mostly after we finish. The only type of question you can ask in the middle is like, I don't understand a word or something of that sort. So you can stop him, but not for major interruptions. And the committee will only ask questions after the public is dismissed. So all that is correct.
Thank you, Gabor. It has been a really fun 5 years, and I've learned so much. So I appreciate all of your mentorship. So we'll get right into this. Hopefully, we will still finish on time. The title of my dissertation is Space Environment Modeling from Extreme Events at Earth to the Outer Heliosphere. And it was a challenge because my projects really cover a large spatial scale. Trying to come up with a cohesive title is a skill. All right. And also changing the slides is a skill. But it's okay. I have the skill. I can graduate. So we'll go through some very brief background, but not very much, because a lot of you have been to department seminars. You've been in our department for a while. And so hopefully you have some of the background you need to get through this. And then 3 chapters, 1 each for the projects that I've done, 2 of which are completed papers and 1 of which is almost a complete paper, and then some conclusions and wrap up at the end. So first, I want to talk about the tool that I'll use for all of these projects. This is the Space Weather Modeling Framework, which has been developed mostly here at Michigan and at collaborative institutes. This is absolutely a powerful tool of the space physics community. It is a software that allows us to couple different numerical models, swap out numerical models, have them all talk to each other and work in one cohesive system. And so we have this lovely flow chart that shows some of the many things that we can do with it. I only used a small portion of this for my own projects. The outer heliosphere component, which is not highlighted, and then all of these green highlighted components for the second 2 projects. This is a very, very strong community tool and a powerful capability for studying space physics. All right, I want to cover magnetic reconnection because it will feature prominently in this. In this case, we have a complicated diagram on the right for the space side, and on the left, we have the climate side diagram. If you haven't seen reconnection before, the idea here is that we have magnetic field lines that are connected to different places. Maybe they're connected to the solar wind, maybe they're connected to Earth, and each end of the field line is connected to one of these. When they come close together, the ions that are following those field lines, the trapped particles, and the electrons will diffuse across. They will decouple from the magnetic field lines. They will no longer be frozen in, and they will be able to switch connectivities. And at Earth, what this means is that the solar wind can connect to the Earth via magnetic field. This process releases energy and creates high-speed jets. There's inflow from the sides, outflow up and down. In this case, it can be rotated 90 degrees if you're somewhere else. But this is a very simple picture, so when we talk about this later, Know that this is very critical for energy and flux transfer into and out of the magnetosphere. And finally, Earth's magnetosphere. I've said it twice now, and I'll just put up this diagram very quickly. The Earth has an intrinsic magnetic field generated by an internal dynamo. That magnetic field extends out into space and interacts with the magnetic field coming from the sun embedded in the solar wind. In this simple diagram, you can see kind of the shape of this, how it's compressed on the day side. The sun would be all the way to that side. And on the night side, it gets dragged into a long tail. Hopefully, a lot of this is familiar. There are some features. There's an upstream shock. Reconnection happens on the day side and the night side, which we'll talk about a little bit later. And then there are a whole host of various plasma environments and electric currents that call this wonderful place home. All right, on to the first project. So this is the MSWIM 2D, the Michigan Solar Wind Model in 2 dimensions. This paper has been published in the AppJ supplement, and this was a couple years of work. This happened during COVID, and this was my Learn to Code, Learn to Model project. So it took a little longer, and I appreciate Gabor's patience with that, especially virtually. For those of you who remember Blue Jeans, that's definitely a trying time. So this diagram is a very rough cartoon of our solar system, the heliosphere, the area of the sun's influence against the interstellar medium. In the center, there's cartoon orbits of the planets, which are to first order coplanar in what we call the ecliptic. And then around that, there's a termination shock where the solar wind emanating out becomes subsonic. There's the heliopause, where the solar wind is no longer the dominant population. And then outside of that, there may be a bow shock or a bow wave. As the sun moves through this environment, it interacts with the interstellar neutrals. And unfortunately, we don't have a lot of observations of this. We launch spacecraft that are very few and far between, and we can see the planetary magnetospheres interacting to the solar wind. We can see our few spacecraft, but space is vast, and the heliosphere is a large volume. So with limited spatiotemporal coverage, numerical modeling is necessary to fill these gaps. I will also note that some of our planetary missions operate inside the magnetospheres of other planets and do not actually capture the solar wind that's driving those systems. So modeling can be important as well to know what the input is if we're only measuring the output.
Excuse me, online audience cannot hear you.
That's correct. The Zoom link did not work, and so there is no way that they will be able to watch this until the recording afterwards. Yeah, I apologize for those of you who are watching this in the coming days and weeks. If I can figure out how to send a terabyte of video recording. So just a little more basic idea. The solar wind, as it comes out of the sun, it expands radially outward. And for the most part, it is directly radially outward. There's very small deflections from that. This is the quiet solar wind, the background solar wind. And as it expands outwards, it drags the magnetic field from the sun with it. Now, the sun itself is rotating. This is seen from above. This would be the North Pole, from the north geographic pole of the Earth's perspective. So the sun is rotating counterclockwise in this figure. And as it rotates, the solar wind is expanding out, and the source of a single region is changing in azimuth. So you wind up with this spiral shape that connects the same source region as it moves around the sun. What does this look like when we model it? So the far image over there is the entire simulation domain of this project. We're simulating the outer heliosphere in 2 dimensions, and we're going from 1 AU, the orbit of the Earth, all the way out to 75 AU, which is way, way beyond Pluto for reference. Pluto is about 35 AU, give or take 5. Zooming in, you can see that Parker spiral developing as the inside rotates. And I've marked the sun, not to scale, the Earth, definitely not to scale, and then some other object that's out there in the simulation domain. So how do we get the solar wind at one of these objects? Well, the previous model that came from this group, it used a code that Gabor wrote called versatile advection code, and it did 1D propagation. So we take the input and we send it out in a line, and we find what the solar wind would be as it evolves using 1D physical equations when it gets to whatever your target object is, say Mars. In this case, note that the Earth here, where we're making our observations, and whatever planet are not aligned. So the solar wind that we see at Earth is going to completely miss that planet under normal circumstances. However, if we assume that the solar wind variation over the course of a solar rotation is relatively low, so the high speed and low speed streams are relatively constant, don't change over time, high density and low density regions, then we can actually apply a time shift to that data to get the solar wind at a different azimuth at the same time. So this is what MSWIM did. It took the solar wind, it time shifted it, and it took that time series and propagated it using the MHD equations to get to a target. And it did pretty well. If you look at this, this is, I believe, from Pioneer 10, and speed, density, and magnetic field magnitude. And the propagated and observed, if they weren't labeled, you probably couldn't tell them apart. You wouldn't be able to guess which was which. But errors creep in when you have large separations, because we assume that the solar wind doesn't change over the course of a rotation. It definitely does. This is good to about 60 degrees of azimuth separation, but beyond that, your skill decreases rapidly. So we're going to do the next step. We're going to move this to 2 dimensions. This started from the New Horizons modeling challenge. So predict what the solar wind will be when New Horizons passes Pluto. We're going to use a 2D grid. We're going to add interstellar neutrals, because at large radial distances, the neutrals and the ion population from the solar wind interact through charge exchange. That slows down the solar wind, it changes the density and the temperature, and so this is a very important consideration outside of about 4 AU. And our input can now be multi-spacecraft. So we have observations at Earth, which is at 1 AU, but we also sent the Stereo A and Stereo B spacecraft at roughly that same orbit, and they had azimuthal separations. So we can now drive our model in a more complex way. For the design of this model, it uses a really innovative grid where the ions expanding radially outward from the sun expand on a spherical grid, which makes sense because the sun is a sphere. The neutrals, on the other hand, are not impacted by the solar wind magnetic field, and they are coming in with a constant direction, a constant speed, and instead of flowing on that spherical grid, they flow on a cylindrical grid instead. Because the model does not support multiple grids at the same time, because that's really difficult and not necessary for most things, we actually did a unique trick here where we changed the fluxes going into and out of the boxes, each grid cell, to account for the differences between a spherical and a cylindrical grid. So accounting for, in this little cartoon here, you can see how the ion grid, which is in a spherical coordinate, allows the radial expansion. The neutral grid, which would be this red box, the cylindrical, has the flow basically parallel. And then by changing the phase fluxes, we can allow those to interact. All right. And this is what Interstellar's neutrals look like. On the left, there are different generation areas, with the inner heliosphere being roughly that black circle in the center. And then they come from outside from the undisturbed interstellar medium, from shocked materials, or ones across the bow wave, ones inside the termination shock. So charge exchange can happen at all these points. We have only included 2 of these, which are the most impactful in this model. And on the right-hand side, this goes from plus or minus 10 astronomical units in each direction, and it's plotting the neutral density for the first neutral population. And you notice that there's a cavity where the neutral density decreases as they flow from the far side over towards me, and this is because of charge exchange. So if you're somewhere down here, downstream of the inner heliosphere, your neutral population has a very substantial impact to large radial distance. So for input, we took this spacecraft, if there was just one, and we're time shifting it to account for different azimuth. You can think of this based on the solar rotation. So you can think of this as taking the time series and wrapping it around the inner boundary of the model at 1 AU. So when you have no time shift, does my mouse show up? Yes. When you have no time shift, you could just take that solar wind, propagate it straight out. But if you have an azimuthal separation, then you would need a time shift of about 6 days. The solar wind that was observed 6 days previously has then rotated around 6 days later and reached your point. So in this way, we can fill the entire inner boundary at 1 AU. Now, because the solar wind changes over the course of a Carrington rotation, there is a discontinuity. But fortunately for us, we can also include multi-spacecraft observations, which will also produce discontinuities in the time shifting. So in this case, we have one of the stereo spacecraft located at a different azimuth than where Omni would be. And if we take a specific point here, this point would require a time shift of plus 6 days for Omni, minus 12 days for stereo A. And so we will interpolate between these. We can interpolate between subsequent Carrington rotations or between subsequent spacecraft. We tried different interpolation methods. They didn't make too much difference. So linear interpolation has been the best. And we take the respective time difference and then just pull the value in between. This is a major limitation that we will talk about later on when it comes to magnetic field. And so here's this figure again, and it allows us to go to all kinds of different objects at all different times and all different azimuths. On the right, this is the inside of the simulation domain. Again, the black circle is Earth's orbit. We can go to Mars at the lower left. We can go to Jupiter up above, or we can go to Pluto way on the far side. And because it's 2D, we can do one simulation and extract spacecraft at any of these points. But what does it look like? Does it work well? Here, we're validating against the MAVEN spacecraft, which orbits at Mars. That's roughly 1.5 AU from the Sun, which means it's half an AU from the Earth. Very, very close. The MAVEN spacecraft would occasionally get outside of the Martian magnetosphere and measure in situ solar wind. And this happened, it used to happen more in the past, they changed the orbit. This happened pretty frequently throughout the year. I think the majority of orbits. And so taking that, we can propagate our solar wind measured here at Earth using this model and compare it directly to those observations. And because it's pretty close, we would expect that our model performs well. What you see in these, density is the top plot, solar wind speed is below that, and then the radial component of the magnetic field below that. And then this bottom plot shows the azimuthal separation between the input sources, Omni and stereo A, and the target at MAVEN at Mars. And the performance is very, very good. If you look at a spot like this right here in the middle, you can see it captures the peaks and valleys. It's getting a lot of the density very well. It's getting the radial component of the magnetic field. And important to note, there's a large gap here where the solar wind is not observed by MAVEN. MAVEN's still in the magnetosphere, measuring all kinds of great things there, but they don't know what is driving those phenomena that it's observing. But the model can predict that. So we can use this to fill out especially large statistical data sets. One thing to note here is that the minimum azimuth with the two spacecraft, Omni is almost always closer over this long time span. But at this point where it would get farther, stereo A is closer. And so the amount of time where we have a small azimuthal separation is greatly enhanced by the multi-spacecraft input. So it works great up close. How does it work far away? Well, you don't really get much farther away than New Horizons, which went to Pluto. That's one of our farthest missions and one of the farthest that has very good observations. Now, the horizontal axis is both time and distance. On the far left, it's 22 AU. On the far right, 46 AU. And the top panel being log of density, the middle solar wind speed, and the bottom is pressure. You can do temperature too. We opted for pressure. With these, the skill is a lot less, especially if you're looking at the density, which is now on a log scale, but it is still pretty good. We are getting the right order of magnitude with density. You can see the density decrease over time. The solar wind speed is decreasing slightly over time, and the temperature, the interstellar neutrals are critical to get that. The neutrals are also critical to get this speed. If you remove the neutrals, which we did for testing, this solar wind speed is about 10% higher. And so your curves completely don't match at all. We are getting a lot of the large scale fluctuations with very few misses and a lot of the small scale fluctuations as well. So this simulation is extremely useful for all kinds of targets throughout the solar system. It is also very cheap to run. I did the runs on my personal laptop. But Tim, what if I want to actually change slides? But Tim, what if I want to actually use this? Do I have to learn how to run the model? You do not. I ran the model from 1995 to 2022, and it's trivial to extend. I just have been busy. It is all saved for the entire domain, 1 AU out to 75. The solar wind input was varied based on available spacecraft, and it is publicly available at this web address. Take out your phones, take a picture. So designed this website where you can go put in a satellite, put in dates and times, create the trajectory file for that satellite. Some of the planets are already in there, preloaded. And then you interpolate the solar wind to it. It gives you a quick look plot, and you can download the solar wind along that trajectory and just compare right away. So hopefully that's convenient. There are definitely people who have used this already. All right. Moving on to the next project. This was simulating extreme space weather with kinetic magnetotail reconnection. This is currently under review. It's been under review for about 50 or 60 days. So only two of those weeks have been with the reviewer. So things move at a great pace. All right. So for most of our simulation, we use MHD models, magnetohydrodynamic models. And these have some limitations. Although they're fast and they do very well at many situations, they assume a specific particle distribution. So a Maxwellian or a bimaxwellian distribution. But particles will frequently deviate from this in the real space environment, especially in areas of magnetic reconnection or something like that. MHD models also assume frozen influx, where during magnetic reconnection, the particles are uncoupling from the magnetic field lines and crossing over. And while MHD approximates this using numerical or diffusive resistivity, it's not actually capturing those physics in the equations. So we're going to use what's called particle and cell modeling, PIC modeling, where we actually follow individual macroparticles and do the simulation by solving those equations instead. The PIC model we will use is called FLEX. flexible exascale kinetic simulator that UC developed. It's a wonderful code, and it follows on. It has heritage from iPic 3D, but he completely rewrote it. It is highly efficient, highly flexible, and it has lots and lots of great features that aid in our physics that I don't have time to go into, unfortunately. This has been coupled to a global MHD model of the Earth's magnetosphere. And so you could previously put PIC code right where you needed it, cover an area, maybe where magnetic reconnection would be, in this case, the dayside magnetopause, and put a PIC grid there and only solve the kinetic equations where you need to, because it's extremely expensive. Shen Tong's work took this and made it adaptive. So previously, on the far side, you could have individual PIC boxes where you solved the PIC code in the greater MHD background. But now, Shen Tong made it adaptive so that at runtime, you can activate and deactivate cells within those regions. This is extremely expensive to run the PIC code, and so the ability to minimize your area is critical. I'll go back one slide. Here you'll notice the PIC box covers a large swath of the magnetotail, but wouldn't it be great if we could only cover the places where those frozen-in conditions are breaking down? And so in this case, we're coupling this model to the MHD code, and information is sent from Batsaras, which is our MHD model, over to Flex, initializes the particle population, both do the computation, moving the particles or the fluids forward in time, and then the PIC solution calculates moments and sends them back to the MHD, which overwrites it. The MHD code, for its part, calculates local criteria to activate or deactivate the PIC cells, and then sends that back over to Flex so that we can select regions that are only interesting. So for this, we took the criteria for selection that Shen Tong used, and we expanded them a little bit. So we're mainly focused on magnetotail reconnection in this study. And in the plasma sheet, we want to make sure that we're only running PIC in the current sheets. We want to distinguish X lines from O lines. So modeling a flux rope is not all that interesting, but modeling reconnection is. We want to make sure that we're getting the main current sheet across the tail and not the magnetopause currents, excluding the solar wind using specific entropy. And we want to also exclude the magnetosheath because we were activating some areas up there that we didn't need. And so we keep the velocity low. After these criteria are calculated, they are passed from Batsaras back to Flex, and a buffer is applied around the region. So more PIC cells are activated than just the ones that meet these criteria. This is important so that the particle distributions can build up and drift away from Maxwellian, and also some of these are pretty restrictive. And so we want to be more permissive than that and actually capture those features. So I know some of you out there are shocked that we keep the speed less than 900 kilometers per second. But Tim, the outflow jets, don't worry, they're captured in the buffer. For this simulation, these simulations, we set up a pretty standard space weather modeling framework magnetosphere grid, as shown here. We then applied a PIC grid inside the pale box. In the paraboloid box, we restricted it further geometrically, which is a feature that Flex allows. And then in the red, this is a sample time where only the reconnection sites are selected. So you can see how if we were doing this simulation with just PIC, we would have this enormous area to cover. And now we've been able to restrict it greatly, which greatly enhances our ability to get through the runs. For this study, we are interested in the most extreme space weather events. These are the ones that are the most geo-effective. They impact our technology, our health, life on Earth. They induce currents in the ground, and they kill our satellites. So the far image is from Salem, New Jersey, where a $8 million think $8 million transformer burned out in 1989, Hydro-Quebec storm, and that thing can't be replaced overnight. In fact, that thing can't be replaced in 3 months. So these are very, very important to understand. Here are the Starlink satellites burning up. Great. And this is aurora that is seen in Hawaii in 1859. Of course, this is a drawing, but I think they're a pretty good artist. I don't know, better than I am. So studying these events is critical so that we can forecast them, understand the impacts and the causes and the connections between this highly coupled system. And yeah, so we chose 2 events. One is the Halloween storm from 29th October 2003. This had a minimum SIMH magnetic perturbation at the equator of minus 391 nanotesla. For context, 0 is the normal quiet, and a typical geomagnetic storm is like minus 100. So this is about 4 times the SIMH index. We chose a storm 1 month later as well, November 2003, which had a minimum SIMH of minus 490 nanotesla. These are very extreme, way in the tail. In the space age, we have only observed something like 20 or 30 storms that even come close to these magnitudes. The idea here is that having the PIC code will allow us to capture the most extreme events better, because the MHD approximations should break down under these extreme conditions. All right, so I'll play a little bit of this movie for you. And this is what the simulation looks like. This is the XZ plane of the magnetosphere, and you can see reconnection happening on the tail, sending plasmoids downstream all the way out those doors. And at some point here, the PIC will activate there. So the black box is the region where we're solving flex, where we have that coupling on. And it's selecting the plasma sheet, it's selecting those X lines, and the reconnection is captured with kinetic physics. So in this diagram, you can see the differences between the kinetic reconnection and the ideal MHD reconnection, which is down at the bottom. So this is the same plot you saw earlier. I've put the white arrow where the reconnection X line is, in this case with the PIC. And you can see the complexities in the tail, all of these swirling little bubbles here, the flux ropes and plasmoids. And this is the ideal MHD simulation. It looks very, very similar outside of the PIC region, but the tail reconnection is completely different. The X line is in a different location. It's less complex. We're not seeing the same features. And on the other side, on the left, there are basically plots of where those X lines are in the XY plane. So a cut the other way. And you'll notice that the ideal MHD in the lower plot is a much smoother X line. It's more continuous, it's smaller, whereas the top one, the PIC creates a very complex structure. But does this impact the Earth? So looking first at the SIMH index for the Halloween storm, the first strong one, the black trace is the observation, and this event has a strange double dip here. And so capturing this has been particularly challenging for MHD models. The amber curve is the ideal MHD. You'll notice it strengthens and kind of sits down here before recovering. The MHD APIC, on the other hand, follows it pretty closely initially, but then it happens to recover. This is a function of releasing a plasmoid down the tail, and it is a consequence directly from the kinetic physics that we're including for reconnection. It stays pretty well, it's closer here. It does pretty well, and then it does experience a second decrease in the SIMH index. It recovers too quickly, but at this point, having those kinetic physics becomes less important. When we look at high latitude indices, both models perform extremely well. The top panel shows the SMU and SML indices, which Their difference is the SME index in the bottom plot. These are high latitude auroral indices, and these are capturing the high latitude currents that are entering the ionosphere. We are capturing the perturbations actually quite well for a lot of these. Here, the differences between MHD APIC and regular ideal MHD are not quite as strong, but you will notice that there are some times where currents are created in certain places in one model that are not in the others. Whether or not the performance is strictly better, it is very impactful to have those kinetic physics. We ran a little more than half of a second storm. This is the November 2003 storm, again looking at SimH. And this one had smaller differences between ideal MHD and MHD APIC. We ran this until the recovery period, after which the kinetic physics are less important. You'll notice that on this global low latitude index, the performance is very similar between the two codes. But when we look at the high latitude indices, we begin to see larger differences, especially later in the storm when it enters the extreme main phase. Here, MHD APIC in red is a lot closer to observations, and it also recovers a little bit better, decreases a little bit better when we move to times where there are weaker currents. So I've shown here that MHD APIC is extremely important when doing these extreme events. It creates different features at different locations and different times. It's capturing those kinetic physics of reconnection in the tail. But considering a 48-hour geomagnetic storm, the kinetic physics take a lot more computational resources. MHD APIC is 25 times slower than real time on 10,000 CPUs. It takes roughly 10 million CPU hours to do one event. For geospace, for the ideal MHD model, it's about 2 times faster than real time on 100 CPUs. So MHD APIC is about 5,000 times more expensive than geospace. What does this mean? Use MHD APIC if you need it. If the kinetic physics are important, if it's an extreme event, if you're considering something where that decoupling is critical. If not, ideal and Hall MHD both do a reasonable job at just a fraction of the cost. So good news for those of you who don't have 10 million core hours in your in your back pocket. All right. The final project has been looking at magnetic reconnection, but looking at it on the day side instead. The idea here, the driving idea, is that reconnection rate, especially on the day side, drives global magnetospheric convection. There are a lot of scientists who are very interested in the worst case scenario geomagnetic storm, a Carrington type event, one that will knock out our power grid for 6 months. But we don't have any observations of that. There are a lot of assumptions that go into it. And so if we can model this, we need to be able to validate those models, and we need to apply them to those extreme conditions to see if there's any sort of worst case scenario or maximum event, some sort of saturation of this day-side reconnection of the driving of the magnetosphere. So in this study, we're exploring the day-side reconnection rate, and we're using different physics. So ideal MHD versus Hall MHD, which separates the ion and electron motions. And we're also going to use an idealized magnetosphere and systematically vary the solar wind driving. Another grid resolution plot. We applied a very high resolution region to the day side, right where the day side reconnection will happen. Because this is an idealized magnetosphere with no dipole tilt and that sort of thing, it's symmetrical, which is good. We used an asymmetric grid for our method of calculating the reconnection rate. This did not introduce interhemispheric asymmetries in the simulation, so do not worry. To calculate reconnection rate here, we tried to use a novel method that Hongyang used first, at Ganymede and apply it to the Earth. In this case, reconnection can be a little bit messy. It can be very difficult to locate field lines to calculate a reconnection rate, or using some derived quantity, something that's been run through a coupler or something like that. So instead, we thought reconnection is a topological change from a solar wind field line to one that's connected to the pole of the Earth. And we're going to take a cut right here at z equals 10 RE. This is the XZ plane. You can see the ideal magnetosphere with the dipole that's nicely symmetric. Take a cut, and we took several cut planes, but just 10 is shown here. And then we're going to integrate the magnetic flux in the polar cap at that cut plane, far above the Earth, far from where all the mess is. And so this blue here represents field lines that are in the solar wind. So not connected to Earth at all. The yellow represents connected from the solar wind to the Earth. And these are lines that have undergone magnetic reconnection. So when a line reconnects, it goes from blue to yellow. And so we could integrate along this light blue border here, but that can be messy. You can see it's got this little feature, and integration over there is difficult. But this is equivalent to, everything that flows in has to flow out in a quasi-steady ideal simulation. And that means it has to pass some midpoint. So if we integrate the magnetic flux that is flowing across that midpoint, it should be, under quasi-steady conditions, equivalent to integrating along this upstream line where the reconnection is actually happening. So that's the second term here, the line integral of v cross b dot dl along this. The first term accounts for changes in the area in that day-side polar cap. So area A is bounded by red curve m, blue curve u, and we're taking the time derivative of the magnetic flux enclosed in that. In practice, over long periods of time, that time derivative is 0. So we can safely neglect it. We didn't in this case. It doesn't make much difference. So we ran with a series of solar wind conditions that varied from very quiet, -5 nanotesla in BZ, and -400 kilometers per second in UX. And we took those all the way up to the most extreme, which is -2,500 kilometers per second in UX and -80 nanotesla in BZ for the driving solar wind. We gave this ideal magnetosphere the constant driving for 3 hours, allowed it to reach a quasi-steady state, and then we would take time averages of the day-side reconnection rate over the steady state period and use those to assign to those driving conditions. The goal is to figure out how the upstream conditions impact the global day-side reconnection rate. Here we're showing a plot that basically demonstrates that our method is pretty robust. On the left, we took 3 different cut planes. So z equals 7, z equals 10, z equals 20 RE above the Earth. And those differences, the mean lines are plotted, but you probably can't even see the difference between red, amber, and black. They're so close. So uncertainty from the cut plane is small, at least under these driving conditions. We also changed that midpoint line, M, and based on your choice of that, because of course you have to find the spot where the inflow and outflow is balanced, changing that line introduces about 25% uncertainty under these conditions. This is -1,600 kilometers per second and -80 nanotesla. So pretty strong driving, but not the most extreme. All right. In this figure, on the right, it's the solar wind speed on the x-axis. On the left, it's the magnetic field, and each series is the other variable. So with these, you can see that the solar wind driving is increased. With an increase in solar wind driving, either B, Z, or UX, your reconnection rate increases. What you don't see is any sort of saturation. So unfortunately, we can't say any driving above X is the most extreme magnetospheric condition that we can get. As the driving increases, so too will the day-side reconnection rate, at least until you're way outside of these ranges. We also looked at the cross-polar cap potential, which should be roughly equivalent in terms of the concept of reconnection rate, because it's the potential of that reconnection X line on the day side mapping down to the ionosphere. Now, there's about a factor of 2 difference here that has to do with parallel electric fields. It has to do with numerical diffusion in the simulation and all of that. But the trends should be similar. In this case, we see the same thing. There is no saturation under either of these, and while the increase in reconnection rate becomes less dramatic with each incremental increase in solar wind driving, it does not actually reach a saturation. It is, I wouldn't even venture a guess as to what the asymptote would be from these graphs. One interesting thing to note, we did the same simulation with both ideal MHD and Hall MHD. So ideal MHD being the black curves, Hall MHD being the blue curves, and those rates are substantially different. Especially when you get into the extreme driving, the differences become a lot stronger. So having that Hall term in there makes a significant change. It actually decreases the reconnection rate and hints at saturation a little bit more than the ideal MHD does. So to recap from this, Hall MHD and ideal MHD have similar reconnection rate. Cross-polar cap potential shows no signs of saturation. And to be honest, stronger solar wind driving in these conditions is very improbable. So it seems like we have not actually explored a worst-case storm, because one that exceeds these thresholds may in fact be that storm. Along with this, we found that the method that we used the cut plane with was a little less robust at these extreme driving conditions. This manuscript is in preparation. It's about 80% done, but there's still a little bit more work to do to take those extreme conditions and verify that this is robust. The end goal of this is to take MHD APIC and include the kinetic physics as well. We've done ideal and Hall MHD, but taking those kinetic physics, we will actually capture that reconnection and hopefully get an accurate idea of what that reconnection rate is that we can measure ideal and Hall MHD against. All right, so to summarize these 3 projects, 5 years, 1 slide. For the MSWIM 2D outer heliosphere, we did simulation of the entire outer heliosphere in the ecliptic plane. We saved the results, made them publicly available online, and we had very good validations at both Mars and New Horizons, and this is thanks to the inclusion of those interstellar neutrals and charge exchange. For MHD APIC, we studied 2 extreme storms, 1.5 extreme storms, applying the adaptive kinetic physics to the magnetotail reconnection. We saw substantial changes to the plasma sheet, to the X-line location and morphology, and to global and local geomagnetic indices. I also looked at local magnetometers that didn't fit in this presentation. There is no numerical increase in skill between ideal MHD and MHD APIC. However, the differences are substantial, and even though it's not predicting DST better when you look at the RMSE necessarily, it is capturing a lot of those features better. So using different metrics or breaking it down into maybe a main phase recovery phase would show substantial improvements. And finally, for the dayside reconnection rate, physics matters. Hall MHD produces lower reconnection rates than ideal MHD in all cases, regardless of calculation method. There does not appear to be any sort of saturation, and I'm excited to see what the MHD APIC results show. Some next steps for the MSWIM 2D, we can extend that. I have soft launched the 1985 to 1995 data. It is on the website, but not not promoted, and extending that run to the present day because we have more observations and we can just keep extending the data set. Identifying and flagging CMEs would be a great project for somebody someday because they don't actually co-rotate. The assumption of co-rotation of the input breaks down. And so flagging those, we treat them as co-rotating, and flagging those would be useful to users because that's a major source of error. Also, we were very close to implementing the fifth order scheme, and finishing that would increase the sharpness of shocks, especially at such large radial distances. For MHD APIC, for the extreme storms, of course, adding more events would be excellent. Adding more extreme events, in particular, I'm interested in the 23rd July 2012 stereo A near miss. That was an extremely strong CME that we observed at different spacecraft. And so we don't know the geomagnetic response very well. Some people have studied it. It would be better to study it with kinetic reconnection. And finally, with the dayside reconnection rate, finish the last 20% of that paper. Make the calculation method more robust. Get a firm idea of exactly what the complete error is. And then run with MHD APIC. Figure out the impact of the kinetic physics on the reconnection rate so we can actually benchmark our approximations in ideal and Hall MHD. I have two more slides, and these are not necessarily related to the same research. I did a little bit of math, and I added up the total computational cost over the past couple years. My first supercomputer run was May 15th, 2020, so a great time in everybody's lives. And I have used a grand total of 57 million CPU hours. That is about 800 years on a standard laptop if you ran it continuously. And using the NASA rate of 29 cents per 28 CPU hours, that's almost $600,000, which is definitely more than the rest of my PhD costs together. Most of this is MHD APIC. It's not only the production runs, but testing and looking for things that are, tuning the selection criteria and restarting and all of this. And so I strongly suggest that anybody who wants to use this work very closely with those of us who have. You can save a lot by doing that. And finally, over the course of my PhD, I've been very involved in education activities as well. The goal is to teach someday, and while I won't be doing that immediately after this, I will work towards that as a career goal. Here at Michigan, I taught, graded, or helped write 12 different classes in the past 5 years. And in those 12 classes, there were 822 students. So my career total, including undergrad, is now over 1,000. Nice round number. If I could knock 6 off of there, it'd be a nice round number. I gave 4 guest lectures in other people's classes, and over the past year and a half, I've also served as an engineering teaching consultant with the College of Engineering. As part of that job, I've led education seminars and worked in the education of the GSIs and GSSAs and IAs at the university. I've also done 12 individual classroom observations where I was able to provide feedback and advice to those students as they're teaching. All right. I'd like to acknowledge the funding sources, NSF Prevents Grant and NASA Shield Drive Center, who have provided funding and a lot of computational time. I used both the NASA Pleiades computer and the NSF Frontera supercomputer, and they're, I'm very familiar. I spend a lot of time logged into those. Thank you to Gabor for your advice and patience over these years, and hopefully the projects have turned out well so far. And also thank you to the collaborators and co-authors on these papers that are published, submitted, and in progress. UC Marov, who's not online, because no one is, Gabor, Shentong, and Bertzi. So with that, I will take any questions. Thank you.